because there's something wrong on that, and they have actually sent the personnel to attend to those problems. Okay, so that was the kind of problem they faced. The other thing is that people said that if you have to turn off the generation, then what's the use? Because if that was the main thing, they sought advantage that with the local generation they should be able to get electricity all the time. But if the electricity has to be stopped, then obviously it really didn't serve the purpose. So these rooftop systems, the simple distributed generation systems, they did not click. Okay? And people, they realized that they needed something else. Okay, so around 2000, year 2000, the beginning of this 21st century, we'll say, there was a consortium which was called SCET. Okay, and they actually came up with the proposal that a proposal for microgrid. Okay, now microgrid, everything is like distributed generation only, but now you don't have to really stop the production or the generation of power, so you can actually continue to feed the local loads with that. That was the advantage with the microgrid. So this appeared to be a more promising solution. And the other thing is that microgrid would be a very small replica of the power system. So maybe a few megawatts, maybe some 50, 100 or 200 megawatts at the max, which is much smaller than the typical power system, which is in gigawatts. So it was easy to manage such a system. So they said it will be a small system, it will be a local system, and we can also actually attach several renewable energy sources with it and so on. So they realized that basically this would be a very promising solution. So that is where the I would say the turning point came, and the microgrids, they started becoming very important and popular among people. Now currently, I won't say that there is a very big commercial deployment of microgrids. There are still very few in the world, but we can see that they're going to be expedited. They are going to be implemented in big numbers in the times to come. After certain issues related to their safety, protection, and control are resolved. So there are some pending issues which the scientists and the researchers are still trying to sort out. Immediately after that, they'll start the work of the implementation actually in the field. So they will actually be able to implement more and more microgrids in the field. Now the microgrids, they can be actually two types. In fact, they can be of three types. One of them is the AC microgrid, which is the exact smaller replica of the conventional power system that you see around you. But of course, the control structure, the protection, and so on, it takes a very different form because of many reasons. So it's a smaller system. Okay, there are a few things which are more critical and so on. Okay, and the protection, for example, it becomes a very important issue. The DC microgrid, on the other hand, is basically a recently emerged DC microgrid, has emerged more recently because people realize that many of the loads today are DC loads. So when they actually use AC microgrid throughout and they connect the DC loads there, they need an AC to DC power conversion there, an extra stage. So people said that why don't we have a DC microgrid itself to which DC loads can be connected? So that is basically the driving force, and the DC microgrid, the inception of the DC microgrid. And then people said that why not have both of them running side by side in our house, in our industry, in our offices, and so on. And then we can take a decision whether we want to plug something into the DC microgrid or we want to plug something into the DC microgrid. So this combination actually is called the hybrid microgrid. I'll just show you the structure of these two. So if on the left side you see a DC microgrid where you can see a DC bus which is at the center of the whole thing, and you can see the generation and you can see the loads which are connected to it. There is a small mistake here. There is because this is this should be DC. This is DC. Sorry, AC, and this should be DC on this side because this is connected to the DC bus. And here again, it should be AC here, and it should be DC. Yeah, so sorry about this small mistake here. Yes. And you have the storage like the battery and so on, usually DC, which is actually again interface with the DC bus. So you have the storages, you have the generation, you have the loads, everything which is connected to the DC bus. Mind you, the AC loads are connected again through a power electronic converter with the DC bus. And apart from this, you can also see a connection here with the utility, the main grid, the big grid, okay, through a static switch. But because this is DC and the utility is AC, you need a power conversion state at least. So this is how a typical DC microgrid looks like. But if you see on the right side, this is how a typical AC microgrid looks like. So the center of the AC microgrid is an AC bus. You can see three-phase AC bus. And just like in the DC system, you have some generation, which is feeding power into the AC bus. Of course, solar PV has DC generation, so it must be connected to AC. Okay, and then only it must be connected to. It must be actually changed to AC through a power electronic system before it can be fed into the AC bus. And similarly, you have these diesel and hydro-based systems which are connected to the AC bus. And you also have energy storages which are connected. But here, the energy storage being primarily DC electricity, it must be connected into AC before it can be connected to the AC bus, the central bus of the AC microgrid system. So you can see the AC loads connected here and so on. And here, just like the DC microgrid, again, you see that there is a connection shown to the utility grid through the static switch. And as I told you, the third type, which is a combination of the two, so you can actually have a DC microgrid on the left side, the AC microgrid on the right side, and you have an interlinking bidirectional converter, which actually can allow power flow in the two directions. Okay, so this is a typical hybrid microgrid. Now this is just to basically help each other to work synergistically with each other. So for example, if AC bus has surplus, AC microgrid has surplus energy, the DC one has less energy, it can always take it from the AC microgrid. Likewise, if DC microgrid has more generation than required by its loads, the AC microgrid actually can draw power through this centrally located interlinking converter. By the way, you could have I have shown the utility grid connection here on the AC microgrid side, but actually you could have it on this side as well. Okay. Now, typically when the utility grid is connected to the system, and this could be with the individual AC bus, AC microgrid and the DC microgrid also. So whenever you have surplus energy generation in AC or DC microgrids, you can always pump it back into the utility. Okay, so you don't need to store the energy. You don't need to waste the energy. Utility, as you know, is an infinite buffer. It can sink or source any amount of power. So utility grid can accept all that power that you're not able to spend in your microgrids. At the same time, if the microgrids are falling short of power, the loads are demanding more power than what they can supply, they can always take it from the utility. Now, this actually leads to two very important concepts, which are the grid connected and the islanded mode of operation. So what you see here are the two modes in which the microgrids operate, and the static switch, which I showed in the previous diagram, is this one. So this is the static switch. Now, in the left, in this case, okay, what you see is that the utility grid is actually connected to the microgrid is actually connected to the utility grid, and this when the microgrid is operating in this manner, connected to the utility grid, it's called the grid connected operation of the microgrid. And when it is not connected to the utility grid, this connection is open. That time it is called the islanded mode of operation, which means that now this part is lit up, it's powered, there's no problem. Unlike the 1547 time, this is not the case here. So you can actually have an island here, which means that if you're looking from the sky, like a bird view, you can see that in the night, for example, this all will be lit up, this area, while they'll be dark everywhere else. So that gives you a feeling of island, and that's why it's called an islanded operation. But now note that it is not connected to the utility grid. So suppose there is a deficit of energy generation than demanded by the load in the islanded operation. Basically this microgrid has nowhere to go to, because the utility grid is disconnected. So it cannot really take that deficit power from the utility grid and supply to its load. So there is a problem. Problem is that now it should probably shut down some of the loads. It can only supply probably the emergency loads, and that also on a priority basis. So islanding leads to many issues. The other thing is, you see that in the left side, which is the grid connected case, the utility is connected to the microgrid. So you can see this VPCC voltage and frequency can be directly controlled by utility grid. Utility grid is huge. So its voltage and frequency, they hardly change. That's what is the assumption. So they do change, particularly in some of the countries, like including ours, they do change a bit, but not much compared to some other smaller systems. So that is what is regulating. And this rest of the inverters systems or the converters, they just work in current control mode, just keep feeding power into the PCC. Okay, here there's no problem. If there is any deficit, you can take from the grid. If there is any surplus, you can give it to the grid. So this is a very nice situation. Control is easy and flexible. Okay, and you can really do a lot of things. But here in the islanded operation, because the grid is not there, there is nobody to regulate. So first of all, you need to have your own source to basically regulate the voltage and frequency on the microgrid bus. That's one very major problem. The other is that you do not have any surplus or deficit reservoirs. Okay, and hence you must resort to load shedding. So now in the islanded mode, therefore, because there is no support of the main grid, okay, what you will find is that if there is a problem, there is a difference between the supply and the demand. So if the supply is more than demand, that means you have surplus. If you have the demand which is more than the supply, then you have a deficit generation. In both the cases, there is a huge problem. Okay, this might lead to, for example, on the microgrid bus, it will lead to frequency fluctuations, voltage fluctuations, and it can cause other stability issues. And it is this point of explanation, this point of my lecture, that I welcome the storage, energy storage into the system. So at this is the time when the need is felt for the energy storage, and I'll just tell you how this can be done. But now because we talk about stability and other things, let me just briefly tell you about the conventional systems first, the conventional power system, because they will actually help us understand some of the things that happen on the microgrid. Okay. So in conventional systems, we all know in our regular, the conventional grid that we see around us, it's all powered by synchronous generators, big large generators at huge power plants. Okay, then they are the ones which are actually generating this power and basically passing it on to the grid. Now what happens if there is an increase of the active power demand on this main grid? Okay, there is a tendency for the synchronous generator to slow down. It slows down. Okay, now that is a natural thing that happens, which you can also see it as in another way. You can say the synchronous generator, it actually offers an inertia, okay, to the system, which is against this reduction of frequency. Okay, so that is the very important point that we need to understand. So this basically leads to what happens, a reduction in the system frequency, all right, okay, which is handled probably through some secondary control, like the governor system of the synchronous generators, where what they will do is they will open up the steam valve, they will actually inject more steam, and they will restore the power back. So they'll actually start generating the active power demand that is there on the grid, and the synchronous generator will come back to their original speed. This is how it will work. But the advantage here, because of the system inertia, the inertia mainly offered by these large rotating mass offered by the synchronous generators, these conventional systems, the rate of change of frequency, which is actually commonly called as Rokoff, is small. You do not have a very high change in the rate of frequency because because of the presence of these synchronous generators. They're like big elephants which are sitting, which are not really moving, and it's not easy to move them. It's like that. So they offer a large inertia to the system. Now, if you look at the microgrids, as I told you, their structure, they are all generally powered by small hydro maximum or maybe some turbine, but majority of them are PV and wind systems. And they're all power electronic systems which are feeding power into the grid. So basically, strictly speaking, unlike the conventional system, there is hardly any inertia. So if there is any change of power, any fluctuation on the grid, microgrid bus, then the microgrid tends to really go haywire, and there might be chaos. So we need to control that. There is no inertia in microgrids. There is no inherent inertia in the microgrids. So now, for example, during a voltage or frequency disturbance that may typically arise due to the supply-demand imbalance. Now I'm coming to the problems of the microgrid. So if you see the islanded microgrid, okay, the supply-demand imbalance can be there. It's very, very common. And you need a very fast corrective action to prevent the collapse of the entire system. And the ROCOF, remember the rate of change of frequency is high, can be high in such systems because there is no inertia. So the frequency of the system can change much faster, and this adds to the stability issues with the system. So the frequency control and the coordination with other distributed generation sources is not present in a microgrid, all right? The increasing power demand, what it will do, it will cause the unequal sharing of power among the various DGs, distributed generation sources like the PV and the wind. Okay, and some of them might get too much overloaded, and some of those might become too lightly loaded. That kind of situation might come, and some of them really may go bad because this very unequal and very high power that they have to contribute. In conventional systems, this sharing and coordination happens because of the inherent group characteristics of the synchronous generator. Okay, so I'm sure there are some people who read about the group control and they know what I'm trying to say. In the renewable energy based systems such as the microgrids, this feature therefore must be added separately. You must add group, you must add inertia, you want to add maybe impedances, okay, to the system to be able to control the microgrid system under these situations such as the demand supply imbalance. So this is just to jog your memory a little bit, people who are aware of the group control. So this group control is basically a centralized control, not using any communication between the various generating sources. So what you can see here, that this is a group of the what you see here is a group in the frequency and this active power demand. So basically you can see how the frequency is drooping as the active power demand is increasing. So basically the information about the frequency is has to be fed to the generating system, and then depending on the slope of this, it actually decides what is the power that the active power that it must supply to the bus or to the system, and prevent the unequal sharing. So all the systems, all the generating systems, they actually use this group control, and this is, remember, is inherently present in the conventional system because of the synchronous generators, because of their inertia. Some of these things are automatically there. They automatically do this. Okay, but in the microgrids, where the inertialess systems are there, where the power electronics is used, no inertia, there this has to be actually incorporated externally to the control of the inverters or to the converters, which are actually interfaced with the DC bus, or with the bus, with the microgrid bus, not DC bus, the microgrid bus. So you can see here, this is the second part of the group. You can see the voltage group here. So you can see that as the Q, the reactive power demand is increasing, the voltage is decreasing. So basically the generators have to be told that, all right, here is the information about the reactive power being demanded by the system, and this is the voltage that you must try to, so this is the voltage that we are getting. So this is the reactive power that you must feed to get a specific voltage output. So that automatically happens in the conventional system, but in your microgrid system, if we incorporate this kind of a characteristic, then we'll be able to instill or incorporate stability in these systems as well. So I'll just tell you a little bit about some of these very important things which are done: virtual impedance and inertia, virtual impedance and virtual inertia. Because talking about microgrids, talking about these renewable energy based systems which are connected or interfaced with the grid through power electronic systems, okay, they are very important. So what exactly we mean by virtual impedance? What we mean by actually the inertia? So as you probably can guess, because I just explained inertia to you between the conventional system and the microgrid system, I think you can understand that inertia, virtual inertia is something which is not really there, but it appears to be there. So your system behaves as if that inertia is there, though it is not there. Basically, this is done through control loops. Similarly, it depends on what kind of behavior your bus is having. So, whether it is a predominantly inductive bus, or it's primarily a resistive bus, or it is some ratio or mix of the two, and so on. So that means that if you actually also create an impedance which is not there but which appears to be there, virtual impedance, you can actually again control the power that you feed into the bus. So there is a need to have these virtual impedances in your system. This can actually do a lot of things. It can actually help you with the real and reactive power control. It can actually protect from the overcurrent during the faults. It can actually also correct the imbalances, and it can do harmonic compensation of a system, virtual impedance, I mean. And of course, the inertia part, virtual inertia part, actually can give stability to your system by decreasing the change of the rate of change of frequency, the Rokoff. Okay, very good. So now let me just very quickly show you how a typical, because I assume that this seminar is power electronics oriented, not just power systems. So here is a control diagram, and you can see that there is an inverter which is connected to the grid. You can see the filter components, L filter and C filter, and you can see the grid impedance, L grid. And this inverter is being controlled through the left side diagram that you see, control diagram. So basically, if you sense the I grid, the current that is going out of the filter, I inverter. If you sense that let's say you sense the entire current in ABC frame, all right, and you just convert it into DQ frame, and you can see that there are two outputs which are coming out of this. The one is the direct axis current, which is coming out of the inverter, and the quadrature axis current that is coming out of the inverter. So actually, you can modify these currents. And how you do that, you see in the control loop, which is shown that you have an ID reference and IQ reference, and you actually compare with them the actual the direct axis and the quadrature axis current with them, and based on the difference, you actually pass them on to the current controller, and this current controller gives you a voltage signal, which is then compared, okay, with this fictitious thing. So this ZVIR is there in this control loop, but it is not anywhere in the circuit. But when the control signal will go to the inverter, it will be like cheating the system. It will be as if this ZVIR is actually present in the system. So you can actually, by adjusting the value of ZVIR, you can actually control your inverter in such a way that your I inverter, okay, would behave as if it is having some, it is basically encountering some impedance ZVIR there in the path. So this is like cheating the system. Okay, there is another example where I have shown that how you can use this current and what you sensed, the inverter output current, and you can actually try to do protection. So here, what we've done is this impedance, the impedance that we have inserted. We want, let's say, that at the time of starting of the system, the large current coming out of the inverter and going into the system, it should be prevented. That's what we want, let's say. But we don't want this impedance to be there throughout. Okay. So what you do is you actually create impedance ZVIR virtual, which is equal to ZVIR into e raised to power minus t exponential term. So as soon as the system starts, in the beginning, as you will see, it will be there. But then as the time will pass, this ZVIR term will actually go to 0. So basically at the time of start, it can give you the protection against a large current. Okay. Well, I mean, this could have been done during the operation. So even while during the operation, there is a rise in the inverter current, you can actually model it slightly different. You can actually, at that time, you can raise your the virtual inductor impedance value, and then you can try to control it. So basically, you can use it as an overcurrent protection system also. And the other thing could be that your inverter may be feeding only the positive sequence voltages into the system. It may be low on the negative sequence voltages. So you'll see an imbalance in the voltages that will be appearing across the grid. So you can actually do this virtual system. You can actually do in such a way. You can create the ZVIR. Okay, that you can make the inverter output predominantly negative sequence or positive sequence in such a way that their mix leads to a balanced voltage across what you are actually applying to the grid on the left side. So that is the unbalances. So if there is an imbalance that you might be creating, that can be corrected. And here is another one, which is the one related to the inertia, something I said about the synchronous generators. So what you can see here is that we have, if you see this P reference, the active power reference, is compared with the actual active power that's being supplied by the system. And from the group controller, that slope basically, you can see that what should be the frequency, what should be the power that should be supplying the active power. And so basically based on this, it actually generates the frequency. So that frequency is generated and you actually are able to supply that active power into the system. And the same is the case at the bottom, which is the loop which corrects the voltage. So if there is a shortfall of the voltage is falling on the grid, you supply reactive power and you actually try to shore up the voltage. So voltage will actually again stabilize back to the original value. So this actually you see 1 over JVIR. Now JVIR is nothing but the virtual inertia. You see the left side block, integral controller, inside that you have this J virtual. So that inertia, that constant has come in here. So all this inertia thing is not there. You have power electronic converters. There are no rotating masses in the system. Okay, you can see in the diagram at the top right, there are no rotating masses. But by doing this type of control, you are actually mimicking as if there is an inertia, just like in the conventional system. Okay, so that is the beauty of this particular control approach, and that is why it was very important to tell you. So virtual inertia, virtual impedance, basically to control your reactive power, the active power, and so on. Equal sharing among the various converters. Now I am deliberately leaving out these because they are related to DC grid and they are too particular. So I thought that one example is good enough. Need of energy storage in microgrids. So now at this time I tell you what is the need. So you know now that the renewable energy sources which are used extensively in the microgrids, they have intermittent nature. Okay, so you can't predict their value exactly. It varies with the solar radiation, wind speed, and so on. Okay, so basically you need some sort of an energy buffer to fulfill the power requirement of the customer or the consumer. As these sources they vary, the output or the yields of these sources they vary, and there is let's say a loss of power, or in fact there could be a surplus power also, because I'll just tell you the energy storage not only it can supply the deficit power, it can also absorb the surplus power. So energy storage presence is really a very nice thing. It's a blessing because it can do both the things. So energy storage is basically you can say that it is currently particularly it is the main I would say method. It is the main philosophy. This is the main approach which supports the operation of microgrid and balances out the source load power mismatch, the demand supply mismatch. So this is very nice, and that is why people are talking about energy storage in microgrids. So basically you can say that today's microgrids, they cannot work without energy storage devices. And what are the various energy storage devices? You have the batteries, for example, the lead acid batteries. Everybody knows they're simple to charge and so on, but of course their life is less. Then you have the sophisticated batteries like the lithium ion, but they need more balancing between the cells. You have the nickel hydride, and you have a big range of batteries. You have the secondary batteries or the flow batteries and so on. Then you have the supercapacitors. By the way, the supercapacitor is a relatively new concept. The battery, of course, has a high energy density, but it does not really have a very high power density. So if you actually try to extract power from the battery at a energy from the battery at a very high rate, which means high power, it actually reduces the life of the battery. So you try to basically you need something which actually can supply power, supply energy at a very fast rate without losing its life. So a supercapacitor is one such device which has recently become popular. A supercapacitor, is nothing but, it's a double layer capacitor. Unlike the single layer capacitor, where your charge is only on one side of the plates. Here you have both the sides of the plates, plus the distance between the positive and the negative is very small. So C is equal to epsilon A by D. D is very small. A is made very large because the electrodes which are used, as we use in the battery, here also we use electrodes. These electrodes are porous. And porous means that now you have lots of inside, there are spaces, deep spaces here and there, which actually increase the area drastically. So they can actually have a large charge which can reside on them and cause a very large value of capacitance. So typically you talk about several farads. In the our conventional capacitors, we know that that is actually having a limited value, typically microfarads, right? But here the values of the capacitance are in farads. The only thing is that the voltage capacity is very less, 2.3, 2.5, 2.7, that kind of thing. So each cell has a very low voltage capacity, but a very high charge capacity. Okay, so that is the thing. So basically, if you want to use these supercapacitors for any application, you must connect them in series. And this actually creates a challenge, because when you have to create these supercapacitors of smaller voltages in series, you need to balance them. Because of the large farads, large charge present there can be huge currents that can flow between these different cells which are connected in series, and cause a lot of problems. So to prevent that, you need a very good charge balancing between the various cells of these series connected supercapacitor cells. There is a model which I wanted to explain to you, but then I think there is no time now for that. That's okay. I leave my slides with you anyway. So these are some of the applications that we have talked about, where you need sudden power, where you need pulse power in a very small time. You need a high energy. That is where the supercapacitors are really suitable for. So they cannot replace batteries, because they have much lower energy density than the batteries. They have higher energy density than the conventional capacitors, but much lower than the batteries. So if you really want to use a supercapacitor to run your electric vehicle, its range will be very small. Though it can help with the acceleration of the vehicle up and down, or acceleration in a very nice way, without losing life, because it can give power at a very high speed, high rate, but it is not having energy density enough. So you'll have to charge it again and again. So that is why supercapacitors are not yet ready to be used as the sole energy source in electric vehicles. So this is just giving you the porous impedance model of a supercapacitor, because this is used extensively in analysis and simulations. So if you are actually having a supercapacitor in your system and you want to simulate it, analyze it, then you actually use this kind of a model. This was given by D. Levy, and it's called the porous impedance model. Okay, fine. The batteries have more energy density, but less power density. The supercapacitors have less energy density, but high power density. Basically, then it appears that they basically complement each other. So you can have the battery and the supercapacitor, which are working in conjunction with each other. Okay. So what people do typically is that they connect. They have a hybrid system they use, where they use a combination of battery and the ultracapacitor. So the battery provides the bulk energy to the system, while the ultracapacitor, it actually provides the very fast energy requirements. So the transient, short-lived energy requirements, which are of very high magnitude. This is what. So basically, the ultracapacitor is used to supply that. So basically, the battery doesn't have to do that. And remember, if battery has to do that, it will lose its life. So basically, this kind of system increases the life of the battery. So this is a very common thing, very usual thing, which is actually being used currently by many applications. So what you see here is the interfacing of the battery and the ultracapacitor through power electronics. to a DC bus. The first left side example is a non-isolated one because there is no transformer, you can see there. But on the right side, we've given an example where an electric capacitor and the battery is interfaced with the rest of the system in a microgrid through a transformer. So you can see a transformer there, which actually will give isolation, galvanic isolation. So many applications, they actually expect and they demand galvanic isolation. This is an example how AC microgrids are interfaced with the batteries. So of course, I mean, through an inverter, you can directly you can convert to the AC microgrid. And similarly, you can see that through a three-phase, there is a three-phase system that also you can easily connect this to the microgrid. All right. So these, what you see on the left side, these are the battery sources. On the left side, these are the battery sources. Okay, so typically now, as I told you, what does the storage is doing? It is providing the balance energy, or it is absorbing the balance energy which is not spent. So it takes care of the surplus and the deficit energy. Now, one of the very important things that it does, the energy storage, that it can also do. So let's say this is being fed here by a battery. Battery energy storage, or you can say battery energy storage, BES is also okay. Okay, so BES, that is the one which will supply power to this three-phase VSC. And what you see here is basically, don't get confused with this. We are just saying that there is some reference which has been decided by another power loop in the system, which decides the ID star and IQ star. Okay, and from here you can see through a PLL, you are feeding this information about the actual frequency of the system. Something which I told you when I was telling you about the droop control. I actually have the inherent droop characteristics which I have drawn and shown you there. So this is one thing which is required here in the current controller, and it is also sensing the three-phase current in the ABC mode, and it is converting it into the DQ mode and then bringing it here. So that is the actual direct and the quadrature current, excess current that is flowing out of the inverter. That's what you are sensing. So you actually use this information to decide what is the active power that your system, this inverter, must be pumping into the system. And it also decides what should be the basically the, I should not say star, but IQ. So this one is actually generated here, this information, as a reference to the PWM controller, which then makes the modulation index such that indeed this same kind of ID and IQ, which you have actually obtained here by this comparison loop here, that is actually flowing and controlling your VSC to produce that current here. So basically, eventually this will become same as this. So you will actually get a 0 eventually. But if there are disturbances all the time, then it will keep failing. So basically this current controller outputs the desired direct axis current and the quadrature axis current. Quadrature axis current will determine the voltage, and the direct axis current will determine the frequency. Remember, direct axis current is related to active power. And I told you that the active power, when it is actually the demand increases, your frequency tends to go low. So that frequency information you are getting from here again, and you are able to decide this ID. Similarly, the voltage will dip when reactive power is drawn. So if you see your synchronous generators, everybody knows that if basically more reactive power is drawn, the terminal voltage of the synchronous generator, it falls. It falls. So basically what you do is that you try to increase the flux. You provided more excitation and then you try to shore up that voltage. So if you remember the phasor diagram and the droop characteristics that you showed for the natural ones for the synchronous generators, that actually showed that. So you actually are giving the information about the direct axis current and the quadrature axis current here. And accordingly, the modulation index is actually adjusted to such a value that eventually your three-phase VSC, it gives out, the required ID and IQ here, so that your PCC voltage here, it gets the right amount of active power and reactive power. So that is the point. That is the point. So basically all the converters, if they do like this, then there would be a nice equal sharing of power among them, even when there is a disturbance. There is a sudden change in the power requirements or sudden dip in the power requirements and so on. So this is the combined voltage and frequency control, and this can be very easily managed through a battery source. Okay, so that is the point. Anything that is deficit, because the main microgrid is having some trouble, it is not able to meet the demand, it is not able to, therefore its voltage and frequency are getting disturbed. You actually have this arrangement which will pump the required extra active power or the reactive power and ensure that the V and the frequency don't get disturbed. So improvement of the stability of the microgrid this manner. So that is how the storage helps. Here I have just tried to expand what I told you earlier, that battery is used in conjunction with the supercapacitor. So what you see here is a supercapacitor source. What you see is a battery, and through a bidirectional converter you see that they are connected to a DC microgrid bus. By the way, I just written DC microgrid, but I can actually say this could be the DC link rather than the microgrid. And then basically, you can actually convert this could be connected to an inverter, and this could be connected to an AC bus or AC load. So this may be the case. So you can see that this battery would actually regulate the VDC, okay, through these control loops. At the same time, if there are any requirements of very fast transient currents here, they would be supplied by the UC through this particular system, this control system. That is what it supplies, and it actually prevents the battery from deterioration. So this is the structure for the control structure for the ultracapacitor system, how it is interfaced, and this is the one which is for the battery system, how it is interfaced. So these are the control aspects which I need not really tell you. This one here, this slide is important. That it talks about a very important concept called the LVRT. So with the distributed generation, in some countries like, for example, Germany, these LVRT rules, they became very important, and they were emphasized actually quite a bit by the law agencies. What actually means is low voltage right through. So if suppose there is a system, whether it is a main grid or it is a microgrid, so there is some power source which is feeding power into the grid or the microgrid. Okay, and there are more such systems. Let's say these are big systems. There are at least some 100 to 200 megawatt systems which are feeding power like this. So now what happens on the grid? Suppose there is a fault and there is a sudden problem. The voltage will fall down. Okay, this PCC voltage will fall down. This PCC voltage will fall down. So what happens currently, as I told you before, that it will try to disconnect the system, will disconnect from the grid. This is that static switch. It will disconnect from the switch. But now the same thing the system will also do. The same thing the system will also do. So basically their generation, which was going into the grid, will suddenly stop. So even if there was no fault and it was just a false alarm, what will happen because of this? Suddenly this withdrawing its generation and cutting off from the grid, there will be a chain reaction. Other systems will also cut off. So to prevent this collapse, the sudden unstable situation, okay, it is required in the LVRT that the system actually remains connected to the grid for at least for a few seconds. So that, of course, that number of seconds, it varies from country to country and the standard to standard. But let's say 1 or 2 seconds or 4 or 5 seconds, and during that time feed reactive power. So remember, feeding reactive power, whether you see the conventional generator or what I just explained to you about the voltage frequency control, I told you that if you feed reactive power, your voltage will actually stabilize, should stabilize. So they say that don't disconnect immediately. For a few seconds, try to pump the this reactive power into the system, suitable reactive power into the system, so that this voltage can come up. So if there is no fault, this will actually come up after some time. But if there is fault, it will continue to be low, and then you can disconnect. So this is the very important aspect of LVRT. that we see. So this is just what we have done is it's a detailed reference current calculation that how much reactive power during the LVRT we should actually inject into the system is being actually computed here analytically, and then it can be actually given to this. Basically, this is what will be used by the controller and to adjust its reactive power injection into the system. And one more example which I want to give you is of the peak load shaving. So there are many microgrids. Let's say they are actually having a 50 megawatt average power demand. Okay, but for a short time, it goes to 60, let's say. So this one here, what you see here is that higher power demand for a short time. Okay, so if you have the energy storage in your system, what we can do is instead of expanding our infrastructure to handle 60 megawatts, okay, what we can do is we can actually have a 10 megawatt system, capable system, the energy storage system, which we can put in our microgrid. And what it can do is it can provide that 10 megawatt of balanced power. The rest 50 watts is coming from the microgrid anyway. But this can provide. So basically, your infrastructure as far as the microgrid is concerned, you don't have to update it to 60 megawatt. It will be much more expensive thing than just to use this small difference between the two, the 10 megawatt system, to be actually inserted here. So as you can see here, this ESS, the energy storage system application, as far as this particular example is concerned, is actually called the peak load shaving. It is able to shave off this extra load on the microgrid by supplying power during that time. So you can see that this is the time when the energy storage is discharging, and this is the time, the lean period, that is not much power demand is there when the energy storage is being charged. So you charge it during the lean period, and then during the peak demand, which actually peaks up to 60 megawatt, you let the ESS give energy to the system. So that is how you can actually handle this situation. There are many such examples are there, and I can probably speak for hours and hours and hours on this, but I just gave you a few examples for showing the advantage of the energy storage in microgrid. So basically, it really helps us in the stability, it helps us in improving the quality, it helps us in overload current protection. Okay, it can help us in the compensation, like if there is an imbalance in the voltage. Okay, it can help us with the peak load shaving, and not to forget, it can help us with the voltage and frequency stabilization. Okay, whenever there is a disturbance on the microgrid, arising out of the imbalance between the load and the demand and the supply. These are some of the references which I have used. There's a large number of references. In fact, I was in a dilemma which ones to use and which ones not to use. There are very beautiful papers people have written. Wonderful, a lot of information is there in that. I'm sorry that the connection broke in the middle, and that broke a little bit my flow also. I don't know, I tried a bit, but I'm now inviting you for questions. Please feel free. I think some of the things, if they have not been very clear, will probably get clear during the question answer session. I stop here, and now I request your questions. So please, you can ask me questions now.
Thank you very much, sir. Participants, if you have any question, please answer, or please ask the question. Please raise your queries.
Sorry, Shabir, I exceeded my time actually a little bit.
Hello, sir.
No, it's very fine, sir.
Okay, because it has become almost 1.5 hours. I thought I'll speak.
Hello, sir.
Yes.
Hello, sir.
Yes, please.
Sir, good afternoon, sir. Vivek Agrawal, sir.
Yeah. Please go ahead. What's your question?
Yes, sir, I have a doubt, sir.
Yeah.
When microgrid is connected to utility grid, mainly what are the problems can be arranged, sir? When microgrid is connected to utility grid, what are the problems can arise, sir?
No, so there also there could be problems. If there is an increase in the load, you can actually borrow it from the grid. Okay, so the regular, but the problems will be usually of the time that you see on your conventional power system.
Okay, sir. Okay, sir.
Those kinds of problems you will see on the microgrids. on the microgrid at that time. See, these will not be related to usually about with stability and so on, because as I told you, you are able to get the power that you need from the grid if you are connected to the grid, or you can dump the extra power into the. So you won't really have to worry about what will I do with my surplus power, where will I store it? I don't have battery, and how can you have battery of this magnitude, right? So all the conventional problems that you see in conventional power systems, those problems can come. You can just exactly take those problems to be existing in a grid connected microgrid.
Okay, thank you, sir. Thank you, sir.
Any other question?
Anybody else? So you will get a chance to solve your query.
If you want, you can also write to me in the chat message if you have access.
Yes.
That also is fine. If you are feeling that speaking is a problem or some network issues are there, you can write to me in the chat box. Or you can also write an email to me. I'll just send my email address to you. I will just write on the.
Hello. 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 Hello.
Sir, I think again there is a network issue.
Yes. સરનો કઈ અવાજ નથી આવતો. સરના સાથે પેલું કનેક્ટ પણ નથી
So
થતું.
better you call to sir. You participant, please wait for last 5 minutes, and then after we will wind up this session. Thank you.
Sorry, there was again a disruption. Today is a day of a lot of internet disruptions, I think.
Yeah, suddenly it was again disconnected and we
Yeah,
lost the
now it's
connection.
connected, but yeah, sorry about
Yes,
that.
please, if you have any question, please do raise your questions, queries, no matter how basic, how complex it would be.
Yeah, no issues at all. No issues at all. If I know, I'll be happy to answer. In the chat box also, I don't see any queries right now.
Yes, if you can also write your queries. The sir has actually started from the introduction of the microgrid, then gradually he take us to the environment of the microgrid, then he started discussing the virtual impedance, droop characteristics, significance of the droop characteristics. Then again, they have shifted us from the basics of the microgrid to the requirement and the significance of the energy storage device for the microgrid. Then he has also explained the battery supercapacitors, how they can be interfaced, what are the limitations and advantages and impact on the battery and supercapacitor on the AC and DC microgrid. And also he has very good explained very nicely that why the energy storage is helpful in voltage balancing and even for the peak load shaving conditions. So he has covered almost everything that is required for this particular session and what is being expected, probably what would have been expected by the participants.
Sir, there is one question in chat box.
Yeah, I'm replying to that. I have replied to that just now. Okay, so Somesh Chatterjee has asked me a question, how to improve the inertia. So I just told you, you have to play some tricks. And of course, in your microgrids also, you can have some rotational masses. You can have some generators, maybe of lower powers. It's not that, for the fossil fuel, you can have hydro power turbines. They can give. So that, along with the inverters being given that virtual inertia kind of a thing, and then using the impedances, virtual impedances, by doing a combination of these tricks, you can actually get an improvement in the inertia. The size of the battery storage, Niti has asked me how to decide the size of the battery storage. Now, this actually is a very long answer this question has. So I'll try to write to you. If you send me an email, I can answer you this question. The sizing of the battery storage, that's a very long thing. I'll have to basically, it depends on what kind of features you're looking at. Okay, I mean, there are many, that depends on how much energy you want to get out of that. So whether you want it to only compensate or control your voltage and frequency fluctuations, whether it is also required to give that much of energy. See, remember, the battery cannot give any reactive power because it's a source of active energy. But you can control your converters and inverters in such a way that the battery can still manage your reactive power without really giving any net power. So that is how you have to draw a reactive power. So actually your question is, the answer to your question, Niti, is a bit big, long. So I think if you write to me an email, maybe I'll be able to answer your question. I'll try to refer you to something and then you can understand it from there. Yeah.
Yes, sir. I think that requires multiple aspects to be considered.
Right. Exactly.
Based on that, how much autonomy you require, what kind of your objective is, how much amount of the surplus and deficit you are going to cater that. So there are many aspects need to be considered.
Right.
So it is not a simple answer that for this particular size of the microgrid, you can go for this much size of the battery or so and so.
Absolutely.
So it is not one solution that fits for all kind of the microgrids.
Absolutely. Absolutely. So I think Dr. Shabir has really summarized it very nicely. Absolutely, that's what it is.
Okay, if nobody has any question right now, then we can close the session. Thank you very much, sir, for spending and sparing some time from your busy schedule. And you, many of the participants may not be knowing that I'm your student. So it would be very nice to hear you. It would be very nice to listen to you after a long time. And I hope that almost all participants have gained something that may ignite, that may motivate them to work in this particular area. Thank you very much, sir. Thank you very much for your informative session.
So thank you so much, Shabir, and it's really a matter of pride for me that to hear this kind of a compliment from my student, one-time student. You were I still remember you were an excellent and very enthusiastic student.
Thank you very much, sir.
I really want to thank you and the other people who are associated with the organization of this event for giving me this opportunity, this wonderful opportunity to talk to this very vibrant group of audience. If you have any questions, you can please don't hesitate. You can write an email to me. I'll try to either answer that question, or I will connect you, or I will basically give you some reference that will give you the required information. Okay. So thanks once again, and I wish you all the best.
Thank you very much. Thank you very much. And have a good day, sir. Thank you. Okay, all participants, you are requested to join at 2:30 sharp. The third session will be started on 2:30. So please join before 5 minutes. 2:25, you are requested to join the meeting. Till now, we have a lunch break. So we'll meeting you at 2:30. Okay. Thank you very much.
And all are requested to fill up the feedback form of session 1 and 2. Thank you. Thank you all.